Hello, welcome to today's webinar focused on dynamic force measurement. Thank you for joining us. This is Pete Singer, editor of Semiconductor Digest and today's moderator. We have two great experts today. Jim Macy, who's an application expert on advanced manufacturing at the Kistler Group, and he will be our main presenter. But also joining us is Robert Hellinger, who is the business development manager also at Kistler Group. We will have a question and answer session at the end of the presentations. Of course, you can ask a question then, but you can ask a question at any time during the presentations using the chat function at the upper right of your screen. We will see those here in the booth, and I'll read those aloud, and we'll address those as they come in. So, well, at the end anyway. So with that, please welcome, Jim Macy.
Okay, let me get to move this. Just Pete, one question. You mentioned the chat function. Should they be using the chat or the question function? Oh, okay.
Oh, sorry. Yeah, it's it looks like a little question, but it's inside a chat box. It's
okay
on the upper right of the screen. So.
Okay, very good, very good. Okay. Yep. Okay. Hello, everyone. It's my pleasure to be here with you today, and thank you for taking time out of your busy schedules to attend. We are excited to provide the following insight on how dynamic force measurement is driving the global semiconductor ecosystem ahead. Prior to diving into our presentation, I would like to briefly introduce myself. Okay. Shortly after graduating from New York University some 37 years ago with a Bachelor of Science in Mechanical Engineering, I joined Kistler. From that time in the 80s up to the present time, my numerous responsibilities have centered around helping our customers in advancing their capabilities with our advanced technology. I am happily married with my wife, Kathy, and have two sons. Hold on, I got some issues here. I just want to get rid of, okay. Two sons, both presently out of the house, my youngest being a student at Michigan State University. Okay, I get stuff dancing around my screen here for some reason. I'm just going to close it out. Okay. All right. Yeah, sorry about that. Okay. Okay, I'm active in LinkedIn platform and can be reached as highlighted. With me today is my colleague from Switzerland, Robert, who will also provide us with an introduction and some words on the Kistler Group. We will then move forward with our presentation.
Thanks, Jim, for introducing myself, and also a warm welcome to all of the people on the webinar. My name is Robert Hillinger, and I live with my family in Switzerland, and I work for Kistler since 2018. Before, I spent my whole career in the industrial automation area, and I'm excited to combine measurement technology from Kistler with industrial automation, and together with Jim and other colleagues globally, we support semiconductor customers with our measurement technology. We are helping to increase yield and increase machine performance. But before we are going in more detail, let me introduce briefly Kistler to you. Kistler is a Swiss headquartered measurement company. So we are around since more than 60 years. And as you can see on the slide, Jim? Yes, now we can see the slide. So our motto is measure, analyze, and innovate. So our core competency is measurement technology and to deliver precise and reliable results even under extreme conditions. We help and prepare and evaluate measurement results in such a way that our customer can draw the right conclusions from them and optimize their processes. Our products support the technical progress of our customers and lead them to their own innovations. So they gain knowledge out of the data, which is measured, which is then analyzed, and that allows to gain knowledge and innovations. On the next slide, you can see our global footprint. So we are more than 2,000 employees worldwide, headquartered in Switzerland, and as well production in Switzerland and production in Germany and production in the US, where we produce our accelerator sensors. Besides that, production capabilities, so we have a lot of investments in regard to research and development. As market leader for dynamic force measurement, we invest 9% of our turnover into research and development, and we work closely with universities and research centers, and they are widely using our products as well. Here you can see more than 10,000 customers globally. So we support them from our tech centers in Europe, in the US, and in Asia. And besides that, we have own Kistler locations globally with more than 60 offices, which allows us then to support customers throughout the world. And with that, I would like to hand over to Jim for the presentation.
Thank you, Robert. As Pete had mentioned, within this presentation, we've allotted time at the end to address open questions, and we would encourage if there's something not clear or just ask a question, we're happy to address that. Also, I'd like to get out of the way, within this presentation, I will share information from several third-party sources. When the third-party information is being shared, I will display the source on the slide. This way you can verify or get additional information if you choose. We'll start off the presentation with the why dynamic force measurements are important. Then we'll address the what is a dynamic force sensor, and provide a brief overview on the transduction element. And in this point, we will address some key aspects at the front end of Kistler's production that ensures delivery of leading edge performance with ultra high sensitivity. Then we'll dive into the main portion of today's presentation, the how. Most of the time today will be devoted to sharing examples and solutions of the semiconductor processes. Chip test as well as process monitoring control are done by the utilization today by optical, that's target-based technology, and position, that's motion-based technology. I'd like to point out that the mechanical stress generated within the process is not detectable with these conventional measuring methods, yet it's equally important. Here we have an example on the right side of the screen. A known good die is attached to a known good substrate. While each component appeared to be within good tolerances prior to the bonding process, during the assembly phase, an actual crack developed as shown within the die. Force deviations occurring during the assembly process can lead to quality issues. The next 30 so minutes, I will elaborate more on this, but let us first examine what's under the hood of a dynamic force sensor. Dynamic force sensors utilize piezoelectric crystals. A unique property of these crystals is that when they are mechanically loaded, the stress created on the crystal causes an atomic level displacement, which in turn generates an electric charge on the upper and lower surfaces of the crystal shown. at the top. This electrical output in picocoulombs is directly proportional to the applied force. In the lower portion of the slide, we illustrate the various cuts that we utilize from the crystal. The compression sensing washers are peach color. The shear sensing washers are yellow color. Both of these crystal cuts are utilized in the construction of a multi-component force sensor, multi-component being X, Y, and Z, as shown on the lower right. I would also point out that the crystal washers are directly stacked. Electrodes sum the signals from the individual sensing washers and output their signal outputs. In summary, as the piezoelectric crystal is extremely rigid, the sensor's output deflection is extremely low, and the sensor's output has very high linearity. This high linearity extends across the sensor's measuring range, which is of several orders of magnitude, 1 Newton, 10 Newton, 100 Newton, 100,000 Newtons, all in one sensor. Now let us look more at this amazing crystal. When building sensors, our innovation starts at the crystal level. As the crystal is the sensor's transduction element that directly converts the mechanical applied energy into a proportional electrical signal output, we often grow our own crystals. Under the hood of each piezoelectric force sensor, a crystal is utilized, either quartz or one of our unique piezostar crystals. This selection of crystals allows us to tailor the sensor's benefits, say either in sensitivity, resolution, and/or temperature performance. On the far right, this illustration shows a glimpse of our in-house ability to precisely machine the sensor's crystal, thus ensuring the overall sensor's performance is optimal for our customers' demanding requirements. Okay, in this demonstration, an O-ring is placed on a piezoelectric force sensor, featuring a measuring range up to 10 kilonewtons. That's about 1 ton of force capability. The measuring result is shown in the graph on the right side. In this graph, you'll note that we successfully measure very low force changes within a gram of force. This is easily detected with very high resolution. A unique capability of dynamic force sensors is that they enable one to view small force deviations that are not visible nor possible with another measurement technology. The key takeaways on dynamic force sensing can be summarized as starting with the high rigidity due to the transduction element and its atomic level displacement. This results in high linearity, a wide useful measuring range. Given the lack of movement, the sensing system benefits from a very long lifespan, very high resolution, and repeatability. Dynamic piezoelectric sensors provide very compact footprint size, especially when compared to other force sensing devices. Now, regarding the market, I would like to point out that the market demand for ultra-thin wafers continues. The chip utilization within thin products such as ID chips for credit cards or small-sized chips for AirPods for music. Furthermore, given the latest advancements in extending Moore's law with the evolution of advanced 3D chip packaging and heterogeneous integration of chiplets, wafer thicknesses are required to be at least 5 microns. As shown here, that's smaller than the human hair, white and red blood cells, and even bacteria. Furthermore, I would like to point out that as the wafer thickness decreases, so does the individual die strength, and die warpage increases. With this in mind, I will share how dynamic force is improving semiconductor processes by sensing the stress generated at the tooling and with the utilization of a dynamic force sensor that provides higher resolution, which allows for additional process insight at the physical interface to the wafer and the die. I will cover machining of thin wafers, producing thin dies, handling thin dies, assembling thin dies, and testing. The semicon ecosystem loves to test, so I figured we'll speak briefly on that as well. We will start off with the front end process involving wafer manufacturing, more specifically, the process of CMP polishing and the needs for improving press force accuracy. In the CMP process, I would like to point out two force vectors, as shown here as red arrows. The force required within this process, one force is for the wafer polishing action to the pad. The other force is for conditioning of the pad surface. Within the patent shown on the right, Lam Research recognized the need to improve the downforce accuracy within the CMP and wafer polishing processes. Simply put, they stated the present systems based solely on pressure have their accuracy adversely affected. This is primarily due to friction losses associated with the pressure sensing approach. The patent also provides us a great lesson that when selecting a load cell, one must consider the force sensor's resolution capability. Beyond simply selecting the required measurement range, the need for resolution enables one to sense the smaller occurring forces, say at the pad to wafer interface. Kistler dynamic force sensors provide improved measurement resolution, enabling one to sense the wafer to pad interface. I would also like to share the force sensor selected in this patent only had a fixed 500-pound range. The sensing technology within the sensor lacks scalability, and with it the ability to measure fine resolution. The force sensor had very good 0.1% accuracy, but it was locked in at 500 pounds. Hence, the resulting resolution was only a half a pound, unable to detect the fine pad to wafer interface aspects occurring within this process. As stated earlier, semiconductor chips are becoming thinner. With it, precision within the process regarding wafer flatness remains very important for the individual chip performance, as well as demands for improved process feedback for better process insight and traceability tied to each wafer, let's say for an end customer within the automotive market. Dynamic load cells are installed within these processes, either within the base fixture at the flange supporting the turntable, yet also in the spindle head. This is especially for assembly bonding applications to be discussed later. These dynamic sensors provide an indication of the initial wafer contact or stack up, the actual downforce pressing on the wafer, and live feedback for monitoring and control. Higher performance machines utilize individual force sensor outputs, providing means for live feedback, which enables the spindle head tooling to adjust within the process. Your benefits, higher precision and documentation. So let's take another look at the wafer process, specifically dicing and lamination. and the needs for die tension control during lamination. Here we're looking at a traditional wafer dicing process whereby the wafers are first thinned by grinding and then they're cut into dies. The challenge is that as the workpiece gets thinner, dicing increases the likelihood of. In dicing before grinding, I will only focus on the first 3 steps here. In the first step, in the red box, the wafer is half cut or slotted. This is where dicing is performed. In the second step, shown as yellow film, the back grinding lamination tape is placed over the wafer. This protects the wafer's printed circuit side. In the third step, shown in the blue box, the wafer is flipped and back grinding occurs from above. It is in this step the wafer is thinned and each die separates from one another, then only being held in position by the back grinding lamination tape. Okay, good. In the next slide, we will examine how the earlier process step of lamination influences a later process result with the individual dies. On the left, the wafer is represented and each die is equally spaced after grinding. This is the desired die alignment result. On the right, the tension from the back grinding tape is released, causing the dies to be misaligned after back grinding process. The root cause is noted in improper lamination tape process. Here we have an example of a retrofit solution, whereby the measurement solution has 4 tubular pin-looking sensors installed into the lower machine support structure. It is the instrumented lower structure that supports the darker round wafer contact area. In the upper right, the individual sensor locations are highlighted by 4 red arrows. As the sensors are highly rigid, once they're installed within the mounting bore and preloaded, each sensor can sense a very low force, even the measurement of the structure's internal strain. In addition to the sensor's superior resolution capability, this measurement system provides output signals in real time. This is a desired feature necessary for sensing uneven loading conditions and for control feedback during the film application process. I'd like to mention what gives this measuring system a superior performance begins with the sensor's unique internal proprietary sensing crystal. This measurement system offers a very fine resolution and a high useful output signal. For example, 13 thousandths of a microstrain equals 1 volt output. So now let's look at the back-end process in an assembly process, specifically processes involving pick and place, die sorting, and chip removal, and the needs for die stress control and the determination of proper peeling energy during the chip removal process. Here we show that thinner dies are indeed more flexible. Please see the upper right portion of the slide. I'd like to point out that the gray colored chip flexes as it is forced to release from the blue colored membrane. The membrane's adhesive is detailed in orange. For process reliability, several ejector needles may also be utilized. The ejector needle substructure provides an excellent means for tooling process feedback, for determining proper die peeling energy, and in sensing the process to avoid die cracking. Dynamic force monitoring provides a means for detecting die cracking and the proper peeling energy. I will explain more on this approach in the next slide. Here we know from physics that energy is a measurement of the ability of something to do work. Work is defined as force times distance, let's say in moving a block a certain distance up the ramp. In this solution, the dynamic force sensor is installed within the ejector pin mechanism. This directly measures the effort to remove or peel the die from its membrane. The pin movement is also tracked. On the left side, we view a curve that has the pin position or distance plotted on the lower x-axis, and the pin force, which is the effort encountered on the pin during its movement, plotted on the y-axis. The force performed in removing the chip from the membrane is the integral of this curve, or more simply stated as the area under the curve. The process monitors utilized to track both these parameters provide a detailed signature of the process. A pass-fail toolbox within these monitors provides for waveform evaluation as well as reporting for traceability that is tied to each die removal. So let's take a deeper dive into assembly, specifically thermocompression bonding and the needs for wetting bump pads. In thermocompression bonding, one must control three parameters. They are temperature, z-axis or vertical movement, while assuring proper bond force is ultimately achieved. On the next slide, we'll take a closer look at the control aspects of these three process parameters. Sorry for the lack of resolution on this graph. On the chart, the blue curve is the bond force. The gray curve is the vertical position, and the red curve is the bond head temperature. I will now step through the control steps of these three process parameters. The bond head position moves down, that's coming down right here. The force builds up until contact is made. This is when this occurs right here. That's what we call trigger one, because you know Houston, you've made contact. There you are, you're contacting that. The temperature then is commanded to ramp up. The temperature is eventually held. The solder is no longer solid, it's liquid, it flows, and the bond head blindly moves forward until the force rises. It's right there. Then it's held. So it's made contact with the molten solder. It's assuring that the bump pads are being wet. Next step is the bond head moves in the opposite direction to the desired final spec height. The force signal drops, and the height control is met while the solder is still liquid. In this step, the temperature is commanded to drop, locking in that set spec, and then the force. Of course, you're not even looking at that right now. What I'd like to point out with these two trigger points shown, the dynamic force measurement provides the feedback for the position control, confirming the actual physical contact has been made. The resolution capability of the dynamic force sensor is very important, and the assembly important here, as well as in assembly processes for the semiconductor market. Here we illustrate that the tooling head sensor and provide insight that three sensors, not just one, were utilized. The three separate force signals are required to allow the measurement of warpage and indication of desired parallelism. We also summarize the advantage of the dynamic force measurement system. The high resolution, smaller than 1/10 of a gram, I would also mention good repeatability and compactness, as well as providing real-time closed-loop control. The block diagram also illustrates directional flow and feedback of the main components. In summary, the benefits for dynamic force measurement are as shown on the right. Control, mechanical indication of mechanical contact. The 3 sensors will indicate if proper parallelism is made or if warpage occurred. Increase machine speed and performance because the sensor's rigid, can keep up. And because of that rigidity, it also allows for bonding the thinnest, most brittle materials with improved accuracy. Okay, given there's a lot of testing performed within the semiconductor ecosystem, I believe it's appropriate to close out our presentation with some discussion on electrical testing, specifically process testing involving micro bumps and spring probes, the needs for verification of functionality, and in support of traceability. A concern in testing is to perform the test without damaging the device under test or altering its performance. In this illustration, we have an electrical test being performed on a single micro bump, let's say from a flip chip circuit. On the left portion of the slide, the probe head is shown contacting the individual bump pad for an electrical test, and the result of this test is good. Electrically, this passes. However, we can see on the right portion of the slide, after this electrical test, the bump pad surface is mechanically damaged, a divot results. If this is not caught right away, this chip or batch of chips are later discovered defective during in-service operation. In test probing, it is desired that the micro bumps are not hit with too much force, as this can lead to both mechanical and electrical reliability issues. In this illustration, the shown tooling directly measures both the force and the displacement. Here's the force sensor, and it's shown right here. Connector's right there. From physics, we know more specifically from Hooke's law that if the object applies a force to a spring, then the spring pushes back with an equal and opposite force onto the object. Hence, the force in a spring probe exerts on an object, or in this case, the micro bump, is simply stated as F equals minus Kx. In the below graph, plotted is the force from the spring per displacement of the spring, or as distance traveled. The slope of this force versus distance curve is the spring constant. Next, we'll look at the actual end-of-line testing performed during the manufacturing of spring probes. A Kistler force sensor is shown here, the blue arrow. There's the sensor, it's hidden behind this L bracket. It measures the spring force of every probe spring manufactured. It's an end-of-line test. This test stand also checks each spring-loaded probe prior to its final assembly into arrays and for shipment to customers. By integrating quality control into the automated manufacturing process, bad parts are directly removed from production and the part traceability is maintained. It is well known that testing multiple chips on a wafer requires probe cards to be utilized. Again, the concern is not to damage the individual die contact points during the wafer testing. Here, manufacturers of wafer probe cards must also verify that ultra-low probe force is generated, even when the probe cards are being operated at over-travel positions. Now I'm approaching the end of this presentation. And we'll wrap up the key points on the next slide. So in summary, chemical mechanical planarization, CMP, dynamic force offers improvement of press force accuracy. In wafer lamination, die tension control, die sorting, die stress control, and peeling energy. Thermocompression bonding, initial contact and feedback for wetting the bump pads. Testing phase, contact force on micro bump pads. Dynamic piezoelectric force is critical process value in semiconductor production. With this slide, our presentation has ended. At this point, we'll open up this presentation for replies to questions.
Thank you, Jim. That was very interesting. So yeah, as a reminder, you can ask a question very easily using the little chat function with the question mark in it at the upper right-hand side of your screen. So we have a couple experts here. Please address your questions to them. I do have a question myself, and that is, you talked about a lot of different applications in the semiconductor industry today, but I imagine there are more. Can you explain a little bit, how people, if they have an application they think that could use your sensors, how do they go about getting in contact with you? Do they work with their tool supplier?
Yeah, okay. Yeah, there are. Given the time allotment, I mean, we are utilized as far as more the first part of that question. We are utilized in bonding applications. The fine wires being attached ultrasonically. There's more applications were used. I didn't cover all the bases here, but just really the time alignment. As far as when to contact us, really the best time would be at the offset of the project and really with the machine or tooling builders. To integrate a load cell on a production line is a little more challenging because usually you have to cut metal to integrate the sensor into it. So it's best to integrate it at the offset. Not to say that we do offer retrofit solutions. That's what I showed with the lamination approach. Instead of cutting metal, we're just drilling holes into it, and then we're sensing the strain in the arm or in the structure itself. As far as contacting, my email is Jim, first name, last name at Kistler.com, jim.macy@kistler.com. I think those are the 3 points of that question I recall. If I missed one, just please let me know if there's more open.
That was it.
Okay.
Okay. Let's see. Well, what is the maximum accuracy that you can achieve with your sensors?
Okay. I don't know, Robert, if you want to take that question.
Sure. Yeah. Sure.
Give it the European.
Yes. This is a good question which we are getting from time to time, and you have seen the one slide where Jim is showing the high sensitivity of our sensors, where we can measure really small differences. Coming to accuracy, we publish the accuracy of our sensors and our charge amplifiers in our data sheets. In addition to that, calibration is possible, so that you calibrate each sensor. So that's what's provided from our side. If customers would like to have more details, you have to look always at the complete measurement chain and look at the whole situation. How is the signal used from our charge amplifier to an industrial PC and so on? So what we provide information for our sensor, and we can support to have a look at the whole situation, and then support the customer judging about the accuracy.
Okay, perfect. All right, well, here's a question. I'll just read it. Let you guys try and figure it out. But let's see, where'd it go? Here we go. So that says the measurements are often nearly static. Piezoelectric sensors are not well known for this type of measurements because of leakage current, they say. Is this achieved by the type of amplifier used?
Okay, I'll answer that. Yes, I'm a mechanical engineer. I love the crystal, so I always look at the electrical engineers and the amplifier. This system does have a very small leakage current, and yes, it is associated with the amplifier. So yes, the type of we offer more than one amplifier because of this. There is the amplifier is one aspect, but also the picture I often paint is the crystals generating a charge. You could think of that as like a wet sponge. It's when you squeeze the crystal, you get charge. You squeeze the sponge, you get water. Well, that water is being dumped into a bucket. That's the capacitor. Okay, in the bottom of the bucket, there's a pinhole. So there's this little drip that occurs. That's the root cause of this question right here. So yeah, piezoelectric measurements will not measure static events that occur for days or weeks, because eventually enough water drips out of that bucket that it's significant for the signal that one has generated. So what we're looking at as a manufacturer is, when you bring such applications to us, what we're doing is we're looking at the cycle time. We're looking at how much charge or that water has been generated, and then we're looking at, because of that cycle time, how much drifting has occurred. If it's a small percentage of the signal, green light, we can do it. If it's half of the signal, forget it. And that's part of the reason why we develop our own crystals, because the crystals we develop may have 300 times more sensitivity than quartz. So what we're doing is under a given condition, we're generating it's a huge sponge generating a whopping output that little drip that's occurring it doesn't mean anything. So I'm hoping I answered that question. When you run across these types of applications, it's best to consult with Kistler. We'll review it and we'll actually give you the straight answer, because there's not one answer for this. There's a whole array of sensors that are offered. There's a whole array of amplifiers that are offered. We've been in business for quite some time. Walter Kistler actually discovered this technology, so we've been at it for a while. So we can help you out. Thank you.
Okay, perfect. Well, those were actually all the questions. So would you like to make any kind of concluding remarks today?
Well, I would say, thank you for attending this webinar. We appreciate your time. We're hoping that we can help you advance your technology, and we're looking forward to working together with you. That's all.
Okay. Well, thank you, Jim, and thank you, Robert. I appreciate it.
Thank you.
That does conclude today's webinar. Right. Well, we look forward to having you back. Thanks for joining us, and we will see you later. Thank you.
Okay. Thank you very much, Pete.
Thank you. Bye.